And let's look at the last one, which says significant levels of protein present in the urine is indicative of damage to the filtration membrane. Now this is true because if you look at the filtration membrane, it is formed by the glomerular capillary endothelium. So this is the capillary endothelium made up of squamous cells. Here's the basement membrane. So it's formed of the fused basement membrane of the capillary and the basement membrane of the visceral layer of the Bowman's capsule. So here's the Bowman's capsule. So this is the basement membrane, and so fused basement membrane and the epithelium of this visceral layer. So we have the capillary endothelium, the fused basement membrane, and the epithelium, the squamous epithelium of the visceral layer. Normally, there are very small pores present here. So when when the blood is filtered, plasma with electrolytes passes into this Bowman's capsule. Large molecules such as proteins do not pass through. However, if there was a damage to this filtration membrane, then these pores get really large. When these pores get really large, then protein can pass through, and it will be seen in the urine. Normally, very, very little, insignificant amounts of protein are present in the urine. So we usually say that no protein is present. But when you do see significant levels, it could be due to damage of the filtration membrane. So this statement is also true, and the false statement in this question was this one, and hence the answer to this question. Let's look at the third question, which asks you to identify the true statement, which says vomiting and diarrhea will lead to a rise in hydrostatic pressure. Now this is false, because when a person is vomiting or has diarrhea, fluid is lost. When fluid is lost, hydrostatic pressure decreases, because hydrostatic pressure is fluid pressure. So when fluid is lost, obviously the pressure will fall. So that is this will cause a decrease in fluid pressure. Let's look at the next one, which says edema is seen when there is a decrease in osmotic pressure and an increase in hydrostatic pressure. Now this is a true statement, and again, if we look at this situation here, this image here, this is a very nice image which kind of explains hydrostatic and osmotic pressure. So here we are looking at a capillary, and where it is close to the tissue cells, and this is the extracellular interstitial fluid space, or extracellular space here. So this is the arterial end of the capillary, and this is the venous end of the capillary. At the arterial end of the capillary, blood is flowing at a higher pressure, and that which is hydrostatic pressure, and that pressure is about 35 millimeters of mercury. As it comes to the venous end of the capillary, that pressure drops, and that pressure becomes about 17 millimeters of mercury. So that's the hydrostatic pressure, which is based on fluid pressure. So the fluid flows slowly, so hence the fluid pressure drops to 17 millimeters. Osmotic pressure is based on the solutes which are present in the blood, which means, the proteins and the electrolytes. Now those don't change from the arterial to the capillary end, arterial to the venous end. They remain the same. The same amount of proteins will be present at either end, same amount of electrolytes. So the osmotic pressure is 25 millimeters at both ends. You can see this over here. Now hydrostatic pressure tends to throw fluid out, because the pressure is more, it tends to throw fluid out. Osmotic pressure tends to draw fluid in. So there's a balance between the two. Whichever is higher, that wins. So at the arterial end, you can see that the hydrostatic pressure is more than the osmotic pressure. So fluid goes out into these tissue spaces, and from there it will go inside the cells. When you come to the venous end, because hydrostatic pressure has fallen, but osmotic pressures remain the same, osmotic pressure is greater. So now fluid goes back into the blood vessel. So you lose fluid at the arterial end, but you take it back in at the venous end. And that's how blood volume is kept constant. Now that question said, whenever there is a drop in osmotic pressure or a rise in hydrostatic pressure, that will cause edema. Edema is a situation when there is excess fluid present here in the interstitial spaces, and then that goes inside the cells. So automatically, if the hydrostatic pressure is more, so that means that more fluid will be thrown out. And this could happen in a situation where, let's say, you're sitting for a long time and the veins get congested. So automatically you can see that the pressure will increase. Or you give somebody an intravenous drip and you pour more fluid into their blood vessels. Again, the hydrostatic pressure will increase and it will throw fluid out. At the same time, if you decrease osmotic pressure, that means if somebody was to lose solutes, so they lose proteins and electrolytes, say in the urine or in any other situation, the osmotic pressure has fallen down. So now fluid cannot be taken back into the blood vessel. So it will remain in this extracellular space, interstitial space, and in the cells. So hence it will remain here and cause edema. So therefore, a decrease in osmotic pressure or an increase in hydrostatic pressure will lead to edema. Hence, that statement is true. So let's look at that. So that is the true statement over here. So we said this one was false. Let's look at the third one, which says increased blood osmotic pressure will inhibit release of ADH. Now this is false, because remember we said there are osmoreceptors in the hypothalamus which sense osmotic pressure. If there is increased blood osmotic pressure, that means that usually you don't increase solutes in the body, but it is because fluid has been lost. When fluid is lost, automatically the osmotic pressure rises, because for the same amount of fluid, if I were to give you an example, let's say you have 100 ml of fluid and you had, let's say, 25 grams of solutes. Now, that means now the osmotic pressure is about 1/4. Now, if somebody loses fluid and it becomes 50 ml, but your solutes still remain about the same, or maybe they just decrease only slightly, because whenever there is fluid loss, as in hemorrhage or vomiting or diarrhea, you lose more fluid than you do solutes. So you can see now the osmotic pressure is 50% almost. So the osmotic pressure rises. So there is usually osmotic pressure rises when there is loss of fluid from the body. So when there is loss of fluid, the body wants to conserve fluid, and that will actually cause stimulation of ADH secretion. When ADH is secreted, the kidney tubules will reabsorb water and bring the fluid level back to normal. So it will not inhibit, instead it will cause release of ADH. So this is a false statement. And look at the last one, which says excessive removal of HCl from the stomach as a nasogastric suction can lead to acidosis. This is also false, because acidosis is when the hydrogen ion levels, free hydrogen ion concentration increases. And here you're removing an acid, which is HCl. So you're removing hydrogen ions. So therefore, it will not lead to acidosis. Instead, it will actually lead to alkalosis. It will lead to alkalosis. So this is not a true statement. So the only true statement is this one, and hence the answer to this question.